So, very good evening, Professor Sarvesh Varjurkar sir, and to all our students who have joined us in this All India Council for Technical Education sponsored Prerana scheme to train the students for GATE examination. I am really glad, sir, that you have accepted our invitation and you are here to guide our students so that they could clear the examination of GATE. Let me introduce our guest today. Professor Sarvesh Varjurkar sir is head of the Department of Information Technology in Tulsiramji Gaikwad Patil College of Engineering and Technology, Nagpur. He has also worked as a training and placement coordinator at TGPCD, and he has coordinated several workshops and conferences. He has also worked as a co-NBA coordinator in the Department of Information Technology. He has been training the students and guiding the students for GATE examination since past 7 years. He has total experience of 9 years. Sir, we welcome you with all our heart, and we hope that our students, I am sure, as a matter of fact, that our students will be benefited a lot because of your with your guidance. So may I now request, Sarvesh sir, may I now request you to please continue with your session.
Yes. Okay. Thank you, Sandeep sir. Uh, Regarding
Sarvesh sir,
the
will you please hold the mic a little close? It is your
yes.
voice is not audible.
Okay. Okay. Is it clear now?
I would say better than before.
Okay. Yes. Uh, so very good evening to one and all. Regarding thank you. Basically, I'm going to first thankful, feeling very grateful by the introduction given by Professor Sandeep sir. In this, the main motive for which I have been called over here regarding to deliver the lectures on computer science field regarding digital logic design, in which we are going to cover various contents. As far as the gate perspective is concerned, we'll see about what type of questions may ask in digital logic design, what is the fundamentals behind it is, and so on. Meanwhile, uh, the content of my slides are very clear, which are completely designed with respect to the gate examination. Uh, Firstly, we'll see that in the digital logic design, firstly, we're going to see about this switching network, then combinational as well as various different types. That means one is combinational, another one is sequential, where uh, we are going in brief regarding the digital logic first and design rather. The very first thing that I want to introduce in front of you is the question arises: what is digital logic design? Since digital logic designers, build electronic components where what there are n number of applications for which we are using both electrical as well as computational characteristics. That computational characteristics and electrical characteristics, the design is functional to the field of electrical as well as in computer as well. Ultimately, logical function, and what we can say like protocols, input as well as certain output, and some of the characteristics of these are various characteristics of design, digital logic design, I can say. It is also used to develop hardware, which processes user input and various system protocols as well. One or more inputs, whereas one or more outputs are also be accepted in this switching network. Come back to the next point, that is, what is the significance? What are the various applications for which your digital logic design used for? The answer is very critical or very simple, I can say. Digital logic design are used to design electronic devices such as logic gates, circuits, and other computer chips as well. Uh, what are various? There are n number of different types of logic gates, as we know. We all are quite aware regarding AND gate, NAND gate, OR gate, NOR gate, NOT gate, XOR gate, and so on. These gates are built using transistors. In the upcoming slides, I'm going to explain all this type of things. Basically, in the introduction part, regarding this logic gates and regarding this digital logic design. Firstly, as I have explained about one or more inputs regarding switching network, one or more outputs as well. There are different, again, two different types, combinational and sequential logic gates, as we can say. The output depends on only on the present value of the inputs, whereas logic gates are used. In sequential, the output depends on present and past input values. In sequential, it completely depends on the present and past input values, whatever we have given it for the for that particular calculation. With respect to this digital logic, majority of the things comes in terms of Boolean algebra, where inputs can be calculated with the help of network to get the output called as Boolean algebra. It is used to describe the relationship between the inputs and the outputs. Boolean algebra is the logic mathematics which is used for understanding of digital systems. In mathematics as well as in our digital logics, it is it plays really a very vital role. There are basic operations. As we know that complement means inverse, that means zero's complement is equal to 1, 1 complement is equal to 0. A complement is equal to 1 if A is equal to 0, and if A dash is equal to 0 if A is equal to 1. It means it should be the complete contrast, complement or inverse, or these things, all these three words are one and the same, synonym of each other. While conversion of input to the output with respect to this boolean or this inverse, I can say that if I want to do the inverse of a particular operation, it should be get complemented. There are f for example, in terms of this AND gate, I can say next is AND. A, B, and the truth table. This given diagram stands for truth table, where 0, 0, the value will be 0. If A and B, these two inputs are 0 and 1, the value will be 0. If the inputs are like 1 and 0, again the value in the on the right hand side of the table, it is 0. But yes, if 1 and 1, both the input are 1, A and B both are 1, then your final answer will again be 1. This is the basic simple operation of this AND gate. In that, uh, in that, digital logic designer designs digital systems for which we can use for the test and manufacturability, certain hardware implementations, various simulation. Many of the times we can use this AND gate over there. There are various again different functions that can be used with the help of this logical function that can be expressed are logical expression, and another one is this truth table that I have just now explained, and another form is the graphical form as well. Moreover, in the next slide, in the next slide, what will be the OR type of gate? If this and or are very much contradictory to each other, very much contradictory. Like if you see in this AND gate, 0, 0 is equal to 0, whereas in OR gate, 0, 0 is again equal to 0, but rest all others where there is a 1, the answer should be 1. Over here, where there is a 0, the answer should be 0 in AND gate. Where there is a 0 in input, the answer should be in the truth table is 0. Whereas in OR gate, where there is a 1 in the input, the answer should be 1. As simple as that. Like in the first case, if the input A stands for 0 and B stands for 0, the output will be 0. A stands for 0, B stands for 1, the output will be 1. A stands for 1, B stands for 0, then again the output will be 1. If both 1 are there, ultimately the output will be again 1. So these are the basic operations that we can perform with the help of this OR gate, or the OR gate can perform like this. There are basic theorems. X plus 0 is equal to x multiplied by 1 is equal to x plus 1 is equal to 1, x multiplied by 0 is equal to 0, and so on. This 10 theorem we are going to prove in this today's class, one by one each. Simplification theorem, I can say. In that, let's try with the sixth one first. Xy dash plus y is equal to x plus y, which is already given to you. We simply need to prove this particular theorem where right hand side stands for x plus y. We can with the simultaneous equation I can use like this: x is equal to y plus y dash and y is equal to x plus x dash. X plus x dash and y plus y dash is equal to 1, as if we have already scheduled, I mean, x plus y, it is already proved and it is already in the theorem. You need to, you need to read all these type of things and mug up all these types of things like this: x plus x dash is equal to 1. We can use these particular values over here to prove that LHS is equal to RHS, where the LHS stands for xy dash plus y is equal to x plus y. That we need to prove it. Ultimately, if we can, with the help of this algebra, we can definitely multiply all these type of things to get the next level. That is xy plus xy dash plus yx plus yx dash. Then xy plus xy dash plus xy x dash y will be, get the common from it. X plus x dash will be common. Y plus xy dash will remain outside of the uh, bracket. Again, x plus x dash will replace it by 1. So the answer will be y, or what will be the remaining over here, that is y plus xy dash, which is completely equal to the left hand side of this equation. X plus y, xy dash plus y. That's it. So such type of proofs may be there in terms of question that will be arises in the gate. It can be represented in the next truth table. With the help of truth table, we can again explain various things in this digital logic. I'm going to explain this type of things just hold. Basically, it can represent a Boolean function. Boolean algebra expression can be used to construct digital logic tables for their respective functions. As well as we can also say that the standard Boolean expression or the input and output information of any logic gate or circuit can be plotted into a standard table. The truth table can also called as the standard table for our digital logic, to give a visual representation. What is the purpose of it? At least the simple purpose is there to give a visual representation of the switching function of the system. The table, which is used to represent the Boolean expression of a logic function gate, a logic function, is commonly called as truth table. For any possible input combination, it shows the output value. As if in the previous few slides I have discussed just now over here, this truth table for AND gate and truth table for this OR gate. A logic gate, gate truth table shows each possible input combination to the gate and the circuit with the resultant output depending upon the combinations of the input. It varies according to for which operations we are performing or we are using that truth table. For example, consider a single two input logic circuit with uh, with a normal values like normal input variables, say label A and B. Just now in that and OR gate I have discussed. There are four possible inputs, that is 2 to the power n rows if we are using 2, and 2 to the power 2, where n is the number of input variables. I just now explained A and B, then the value should be 2 to the power 2 rows will be there. 2 to the power 2 rows, ultimately 4. It ranges from, it definitely ranges from 0 to 2 to the power n minus 1, where n is the number of input variables. If we can go for the three input logic circuits, it would have been possible input combinations will be 2 to the power 3. Ultimately, 8 will be the answer. And 4 input logic gate, it will be 2 to the power 4. 5 input logic gate, 2 to the power 5, and so on as the number of input increases. Then the logic circuit with n number of input values would have 2 to the power n possible input combinations for both off and on. For off, we can consider 0. For on, we can consider 1, as if we are in switching network. So in order to keep this thing simple to understand, to understand, we can definitely assume that, or we can definitely mug up that for any given number of input, there will be the output based on combinations. Some examples for the truth table are f is equal to x dash plus yz. For the following, show the following by constructing the truth table. X of y plus z is equal to xy plus xz. Normal mathematical function, I can say. X plus yz is equal to distribute it, x plus y or x plus and x plus z as well. We can also draw certain network diagram for the same, where f is equal to x dash plus yz, x dash plus yz. With the help of this network diagram, will able to solve any different type of input with respect to the output accordingly. This network diagram, again, network diagram will again play a vital role in the digital logic, where the weightage on network diagram is not that much essential in this gate with respect to the gate perspective, but the basic knowledge is also very important. A logical network diagram illustrates what is the network diagram. The picture which is given to the picture which is shown on the screen related to network diagram, it illustrates the network architecture of a group of interconnected computers and other devices such as printers, modems, switches, routers, and many more networking devices, even mobile devices as well. These electronic components from this physical network that can definitely provide uh, or connected through various connecting devices or various connecting networks like LAN networks or WAN or MAN and so on. In addition to this, we can also add a physical network in one area, so that it can connect it to the internet, or it can connect it to provide any we can say online access to all the connected devices. How? How these connected components can be used in the with respect to this Boolean algebra, or with respect to this network diagram, or with the help of this truth table, we'll now see it in the upcoming slides. If the question says that draw the network diagram for f is equal to xyz dash plus xy dash z plus x dash y dash. Now we can see that if the values of inputs are three over here, x, y, and z. On the left hand side, x, y, and z. With three inputs, we have to find all the different possible calculations with respect to a particular network diagram to identify each and every addition which gives you the false result. Which gives you the false result. What that false result will be, how it comes, we have to prove the LHS is equal to the RHS. if we connect all these three things with the help of a particular network diagram, the answer will be F. That is the given answer, I can say. Now, now this X, Y, and Z dash. We'll go with this first. Look, one connection from X, another connection from Y, this OR gate, AND gate, I can say, XY. Along with that, Z dash. The dash stands for, the dash stands for complement of a particular thing. Yeah, inverse, we can say. Like, from this inverse comes over here from the Z, and accordingly X, Y, and Z will be connected with each other to get X, Y, and Z. To get to get X, Y, and Z dash. Meanwhile, X, Y dash and Z. So accordingly, one input from X, Y, one input from X, one input from Y, and the inverse of y, again it is important to get x y dash, and along with that z will remain as it is. Like x and z will remain same, but the inverse of y will come over here to get the negation over here, or to get the inverse over here, to get the complement over here. I can say x y dash and z. Accordingly, if we add x y z dash and x dash y dash, the answer will be x y z dash plus x dash y dash. Meanwhile, x dash y dash, we are interested. We are interested in this two, x y and z dash plus x dash y dash, and after that x y dash plus x y dash along with z will come over here to give the false reply over there. In terms of operator precedence, there should be various parentheses, there should be NOT gate, AND gate, as well as OR gate accordingly. The operator precedence in the board mask, the precedence like bracket open, that is parenthesis, division, multiplication, addition, and subtraction. Same parenthesis we are following over here, almost same, I can say. Same precedence we are going to follow over here. First is parenthesis. Parenthesis stands for brackets. Second one is not, then and lastly will give the preference or precedence to the OR gate as well. In terms of inversion, we can definitely prove these things with the help of the truth tables as well. X plus y dash is equal to, the inversion is x dash y dash. The xy whole dash is again equal to x dash plus y dash. These things I have been proved already, but in terms of gate, they may not ask such type of question. But yes, you need to prove, or you need to use this type of inversion in the gate to solve any different type of problems with respect to digital logic. The complement of the product is the sum of the complements. Whatever the product complement will be the sum of the complement of that product. The complement of the sum is the product of the complement. Complete inverse sense statements are there. The complement of the product is the sum of the complement, and the complement of the sum is the product of the complement. Both are contradictory to each other. Questions might be asked in this type: find the complements of a dash plus b, c dash whole bracket dash is equal to, what will be the complement? We can use by using this particular inversion, by using this particular given inputs, and with this precedence, or with this operator precedence, which is already given to you. Accordingly, you can definitely find out the answer for these questions. Let's see some study problems. We can say, like, draw a network to realize the following by using only one AND gate and one OR gate. but we can simply use one AND gate and one OR gate, as I have already discussed in the very first, previous slides, where we have to find the, we have already find with the help of truth table. AA stands for like and OR. I'm again going to display the table. And OR. If inputs are 0 and 0, the output will be 0. With respect to AND, if the inputs from A and B is 0 and 1, the output again will be 0. In the third case, 1 and 0, it will be 0. In fourth case, 1 and 1, it will be 1 itself. Same thing. In complete contrast, say where there are 1, the answer in the OR gate will be 1. Sorry, the answer for the OR gate by using OR gate will be 1. 0 for 0, it should be 0 again. So 0 0, it is 0, 0 1, it is 1, 1 0, it is 1, 1 1, it is 1. So with respect to this particular thing, we can definitely find out with the help of truth table as well as with the help of network diagram as well. Next, there are various terms that we are going to use it regarding any variables. Say consider variables, for example a and b. Assume that they are somehow combined with and operator. There are four possible combinatorics. I repeat, there are four possible combinatorics where a b, a dash b, a b dash, and a dash b dash. There should not be any more combinations possible if there are two inputs with the help of, or if we are using it with the AND operator. Each of those terms which I have just now discussed, these four terms, AB, A dash B, AB dash, and A dash B dash, each of these four will be called as mean term, or we can say that standard product, which can again be solved by using the network diagram, that do not have to be any complicated, and that they can just be made using simple shapes with short but descriptive notes or labels. But here in gate examination, they didn't ask for any steps, they directly asked for a particular answer. So whichever the method which gives you or which requires less amount of time, we can use that one for our solution. A particular flow diagram, which or if you are using it with the, if you are drawing it with the help of network diagram, that works because it shows the complete flow, as I have already showed in the previous slides, like this. It shows the complete flow from where the input goes to where, from how the input can be connected with the another one, so that you will give you so that it will give you a proper output, and it will satisfy, or it will prove the networks, or it will prove the given statements. Meanwhile, we can also use it with the help of truth table accordingly. Tree diagrams that may also help to show the hierarchy between this we can also call as this tree diagram again. It can be shown with the help of hierarchy between the network components and various tasks and inputs which is given with respect to the question. With the right kind of logic applied, the diagrams can show different kinds of networks, and which is very much transparent, very easy to understand as well, including computer networks. Say we can say the significance, we can say in computer networks, whereas in artificial neural network, the booming topic, these networks and this network diagram are definitely get used, of course, by using some shortest path and many more different parameters. Or we can also say that certain project management networks in many of the organization, among many others, in the in a lot of ways, logical network diagram are often more useful than physical network diagram, because of their ability to show how the things work instead of just showing how the things are connected. It is not only the connection, but it shows how the things works. Where is the inverse, how to pick the inverse, and so on, so forth. This type of diagram does not only show the connection between the network components, it also shows the information about these components and how they function in the larger scheme of the things. How they function in the larger scheme of the things. There are number of network diagram creation softwares applications are also available. If you can simply design, if you simply want to design any particular network design by using various softwares, there are in general, if there are n variables, there are 2 to the power n mean terms. 2 to the power n mean terms, where n stands for number of variables. Look like this. Uh, see, last, see, at last, if if we can list the mean terms for three different variables, say a, b, and c, mean terms there should be for 0, 0, 0 is the input. Definitely, the mean term will be a dash, b dash, c dash. If 0, 0, 1, 0 may be the contrast for the mean term, that is a supplementary goes with a dash, b go with b dash, and c is having the value 1 over there. Accordingly, the answer will be c. Same in the next, for 0 it should be dash, and for 1 it should not carry any dash over there. For 1, all the possible combinations has been given over here in terms of mean terms for three different variables. Now, the question again arises, what is the significance of this mean terms? Mean terms for three variables in terms of combinatorics, a Boolean function may vary and may be expressed algebraically from a given truth table by forming a mean term for each combination of the variable. All the possible combinations have been already been designed and already been explained in the given table, which produces a 1 in the function and then taking or for all the different others and all for the other terms, I can say. For example, the very first function f1, or I can say the first function, that is 0, 0, 0. The combination determined for 0, 0, 1 and 1, 0, 0 as a dash, b dash, c, and a b dash and c dash accordingly. That means for 0, 0, 1 it is a dash, b dash, c. For 1, 0, 0 it is a, b dash, c dash. Each of these mean term results in the expression so that the function can be expressed as, with the help of their designation, even on the extreme right side, the designation which is already given for each and every mean term is m1, m2, m3, m5, m6, and so on. The designation for this three which I have considered now, that is 0, 0, 1, 1, 0, 0, and 1, 1, 1 are m1, m4, m1, m4, and m7. operator means addition, as we know. For operator, there are two possible combinations. Say a plus b, a dash plus b, a plus b dash, and and a a dash plus b dash. Where where each of these term is called as max term. Each of this term is called as max term, or we can say that standard term again, or standard sum again. There are again 2 to the power n different types of max terms for n different variables, since the variable in the max term expression can also be in either it's direct or indirect variable. There should be the choices which are given. There are two. In general, if there are n variables, there are 2 to the power n different types of max terms. The sum of min terms and the product of max terms are dual canonical forms of Boolean function. This min term and max terms are also called as canonical forms as well. Max term is a logical expression, as I have already discussed, of n variables that employs only the complement operator and the disjunction operator. Max terms are a dual of min term. Instead of using and, we can use or over here. And complements, of course. In min term also, we have also used the complements, whereas in max terms we are again going to use the complements as well. In general, uh, this will be the exercise, and this will be the designation, standard designation, I can say. All the different possibilities for three different variables for max terms are by using or operator. 0 0 0, max term stands for a plus b plus c. The designation will be m0. Again, 0 0 1, it is a plus b plus c dash, where the designation is m1. 0 1 0, a plus b dash plus c, m2. 0 1 1, where 1 over here is for complement in this or function, whereas in this mean term, 0 stands for complement, and in this max terms, exactly in contrast, 1 stands for complement. Where there is a 1, there should be the complement, or inverse, I can say. So 0 0 1, 0 1 0, 0 0 1 stands for a plus b plus c dash. 0 1 0 stands for a plus b dash plus c. 0 1 1 stands for a plus b dash plus c dash. 1 0 0 stands for a dash plus b plus c. 1 0 1 stands for a dash plus b plus c dash. 1 1 0 stands for 1 1 0 stands for a dash plus b dash plus c, where we can designate it with the help of m6, and m7. For m7, a1 b1 c1, that equal to a dash plus b dash plus c dash. Accordingly, with the help of this next example, I can now explain or express f in the sum of min terms and product of max terms format. Sum of min terms and product of max terms. There are two different conditions. Sum of min terms and product of max terms. Look, f is equal to a plus b dash a plus b c dash, where it can be true like a plus a b plus b dash, where b plus b dash stands for 1, c plus c dash stands for 1 again. I have to express this particular equation in a big format, and and to express this particular given equation for the same. Any Boolean function that can be expressed in terms of main terms or product of max terms is said to be in a canonical form. Just now I have discussed it in the previous slide as well, over here, where the product of max term is said to be in its canonical form. Form to its other equivalent form, intermediate form, where now with the help of this given equation, b plus b dash stands for 1, c plus c dash stands for 1, a plus a dash stands for 1, and that's why I have ABC is the designation for ABC dash ABC dash designation is M6, AB dash C the designation is M5, AB dash C dash designation is M4, and A dash B C dash designation is M2. Accordingly, I can definitely write all the summation of this designation, and 2, 4, 5, 6, 7 are the summation, and exclusions are like product of max term format is like 0, 1, 3. As simple as that. Where the sum of products, all products are the product of single variable only. All products are the product of single variable only, where where AB dash plus C dash E plus AC dash E dash is should be S, in the A plus B dash plus C plus D dash E, it is again S. Then we have seen that uh, the sum of product, or we can say that SOP, sum of product again stands for SOP, is a standard Boolean expression that sums two or more products, and that for a digital logic circuit, the sum of products expression takes output of two or more logic and gates. In OR gate, we can then together we to create a final and or output. Whatever the sum will be there, we have to create the product for the same. It is simply it is in Boolean algebra in which different product terms of inputs are being summed together. This product is not arithmetically multiplied over here, but it is Boolean. Sorry, as if we can say that it is used with the help of, or it is solved with the help of Boolean logical and the sum of Boolean logical or one and the same thing. Next, we have with respect to sum of products, one or more AND gates feeding a single OR gate at the output. If there are more inputs, more AND gates that can feed addition of these three with the help of OR gate A B dash one design, C D dash E another one, A C dash E dash the third one. Accordingly, whatever the addition and whatever the answer of these products, of these given products, we have to sum it up to get a final answer. Same thing, and again in the complete contrast, product of sum will be there. What is product of sum? Product of sum is the function which is a, in canonical sum of products form. Canonical sum of products form, which means the remaining terms of the function are max terms for which output is false. If the output is false, ultimately the product of sum will exist. These max terms, for example, in the above expression over here, max terms uh, 2, 4, 5, 6, 7, except this, all are product of sum. All are product of sum, I can say. Need to, if we want to solve any particular
Okay, friends, I think that there has been some network issue because of which, you know, we will conclude our class here itself. And for tomorrow's session, we will share the link and the time and other details also on WhatsApp group as decided. Thank you very much for joining us. If you have any queries, of course, they will be entertained in the next session. Thank you so much.